Hopefully you followed my directions and did the warm-up before you are watching this video. If not, pause it, go back, do the first 3 slides on the handout I gave you so that you can practice graphing lines, parabolas, and absolute value functions. So for this first one, and I'm not really going to talk much about this, I think you all can plot a line in slope-intercept form. However, and I didn't ask you to talk about domain and range, but keep in mind the domain and range for this line would be all real numbers. And I also wanted to point out that a couple different ways you can write all real numbers, and one is by using this symbol, negative infinity to infinity, that's interval notation, or you can use the symbol for all real numbers. So the way I graphed number 2, because it was in standard form, so I let x equal 0, we kind of covered it up, so I get y is -5, plot that, then I let y equal 0, solve for x, plotted that, okay? On the next function, you should recognize this as a parabola. So you want to think about the vertex. Remember, we go to the left 1 and down 2, so the vertex would be -1, -2. It is vertically stretched by 2 because of this 2 out front. So that means from the vertex, you're going to go over 1 up 2. You would have gone up 1, but we're doubling that. Over 2, you would have gone up 4. You double that, you go up 8 in both directions. The domain is all real numbers. The range, think about and look at the picture. You can kind of tell that the graph does not go below -2. All the values are all the y values are greater than or equal to -2. So that is our range. By the way, if we put this in interval notation, it would look like this with a bracket, -2, comma, infinity. Then on this one, we have moved to the right 2, but doesn't go up or down, so we have an absolute value graph, so our vertex is 2, 0. And then there is no number out here, it's not stretched, so it's just like a slope of 1, except remember, this one is going the opposite direction, so you can just do up 1 over 1 and graph that. The domain, all real numbers, the range, y is greater than or equal to 0. Interval notation would look like this, if you are keeping track of that. And then on this last one, the vertex would be located at 2, 3. Because of this negative sign, it opens down. However, it's not vertically stretched. So you would locate the vertex, 2, 3, and then you're going to go down 1 over 1, and you're going to go both directions. So remember, we get a V shape. The domain is all real numbers. The range, y is less than, it's opening down, less than or equal to 3. What that looks like in interval notation is it can go from -infinity up until 3, but that's as high as it goes. So that would be interval notation. Okay, so now the new stuff, which is not actually entirely new, this lesson today. So there's going to be a little bit of review to it. We've talked about this type of function. Well, we have for sure this. So we have, I'm asking you to graph this parabola, which of course you could do on your own. So the vertex, we know, is -1, -3. So I'm going to plot that. And then it's stretched by 2, so over 1 up 2. Over 2 would have been up 4, so I have to go up 8. So we get our graph. And then I'm asking you to switch the x and y coordinates and plotting them to graph the inverse. Remember, we just got done talking about inverses in the last section, so we're going to kind of relate that here. So I'm going to list my ordered pairs. Actually, I think I'm going to do this way with a table of values for this function. So I have -3, 5, and -2, -1, -1, -3, 0, -1, and 1, 5. So those are ordered pairs, some of the ordered pairs. Remember, there's infinite points on this parabola. Here are 5 of the points that are on that parabola. And what we're going to do now is we're going to swap the x and y values. So instead of -3, 5, we'll have 5, -3. Here we'll have -1, -2. So this is allowing me to see ordered pairs that are going to be on the inverse of this parabola. So I'm going to plot those, see what I get. So we have 5, -3, -1, -2, -3, -1, -1, 0, and 5, 1. And when you take a look at that, and it's hard for me to draw this on here. Oh, that's not too bad. And we get this. Now, this is the inverse. Keep in mind, if I were to draw in a line y equals x, the identity line, notice that if I folded on that line, I have symmetry. The blue would fold over to what I have in green. Now, also keep in mind, this inverse is not a function. Notice that it does not pass the vertical line test. So that's important to keep in mind. All right. Let me go ahead and I'm going to actually insert a slide. So we had f of x equals 2 x plus 1 quantity squared minus 3. And let's do the inverse the way we know how from class when we did the last section. So I'm going to call this y equals, instead of f of x, I'm going to switch x and y. So I get x equals 2, y plus 1 quantity squared minus 3, and then we're going to solve for y. So I'm going to add 3 to both sides. I'm getting the y by itself is what I'm trying to do. Next I have to divide by 2. Next I have to square root both sides, and hopefully you always remember what do you have to do. Oops, I needed parentheses right there first of all. What do you have to do when you square root both sides? Hopefully you said plus or minus. So we have, I'm just going to kind of reverse this. Y plus 1 equals plus or minus the square root of x plus 3 over 2. And then I can say that y equals, I'm going to subtract 1, but I'm going to put it in the front. -1 plus or minus the square root of x plus 3 divided by 2. Hadn't really planned on this. Let me grab my calculator. All right, so I'm going to go ahead and graph in y1. Let's go ahead and graph this. 2, and then we have x. So you should be doing this with your graphing calculator at home as well, please. And so we'll graph that. And then in y2, now here's the thing, you can't do plus or minus. So we're going to have to do a graph in y2 and then another one in y3. So in y2 I'm going to put -1 plus, and then I want the square root of, and you can set it up like a fraction, and we'll have x plus 3 and a 2. And then in y2, we're going to put -1 minus, and we're going to do the square root of x plus 3 over 2. Now, keep in mind, your graphing calculators only graph functions. So this is not a function. So we have to kind of trick it, and we're going to have to do the top half of it and then the bottom half of it. So now if you hit graph, actually I'm going to go zoom 6 and do a standard window because I'm not sure what I had on there last. There's my parabola. There's the one part, and there's the other part. Now, the reason why you might think, hey, this looks squishier than this other one, keep in mind that your calculator window is a rectangle, and but we went from -10 to 10 in both directions. If you want it to square it off, if you hit zoom number 5, notice it says zoom squared, then it will give you the same, I know squishiness is not, but it kind of does a little better. Now, another problem that this has here, this is an issue with our calculators because of the way it operates with pixels, is it looks like it's not connected right there. It is connected. So it's just drawing, it's supposed to be, if we had drawn this out. So you can graph it even when it's not a function, but you have to kind of know your way around that. Okay, if you have your Parent Graph Toolkit and have room to add one of these, I'm not sure, I think we may have already added the square root function to our Parent Graph Toolkit. If not, you can pause this and copy the information onto your paper. Well, I know you have it in your notes, but you should look for the yellow Parent Graph Toolkit and see if you have room. I think you do. Our parent equation, y equals the square root of x. Here I plotted some values. Notice I didn't use 2 or 3 because I don't want to do the square root of 2. I don't want to do the square root of 3. So I picked values of x that worked nicely. They were perfect squares. And I didn't graph 9, 3 because it didn't fit on my graph. Not really a vertex, kind of an endpoint for our locator point. And for the parent graph, it would be at 0, 0. In general, our locator is going to be located at HK. So we have here our equation generally. You'll notice this looks a lot like every other function we've done. If the absolute value of A is greater than 1, it's going to be stretched vertically. If it's less than 1, it's compressed vertically. If A is greater than 0, it's going to kind of open, it isn't really open, but it's going to be going up or increasing. If A is less than 0, notice it's going to reflect over the x-axis, just like all of our other functions have done. And I have the domain and range for the parent graph, and in general, x would be greater than or equal to h, because if it was shifted over to the left or right. And then for our y value for the range, it depends on the value of k, and it might be greater than or equal to, or it might be less than or equal to, depending on the direction. So if it was this direction going up, then it's going to be greater than or equal to, but whatever the k value is. But if it's reflected because a is negative, then it would be less than or equal to. So that's what we would have on those. Okay, so make a prediction about the graphs of these and then graph them and state the domain and range of each function. I would really love it if you would pause and do that first and then come back, okay? All right, so for this one that I have in blue, notice that my endpoint, my locator point, is going to be located at 1 because it's going to go to the right 1 and up 2. So from 0, 0, I go to the right 1 and up 2, plot my point. And notice the movements I have. Now normally for parabolas, we went over 1, up 1, over 2, up 4. My over and ups got reversed, and that should make sense. Remember how we found inverse functions? We swapped x and y. So I'm basically swapping my over and ups. So over 1, up 1, over 4, up 2. So that's from my endpoint. Over 1, up 1, over 4, up 2. Now, if that is difficult for you, then plug this into your calculator, make a table of values on your calculator, and use the points. I'm okay with that, but this should make sense to you. Then I asked you to give state the domain and range. So for this particular one, our domain is, we can't go to the left. It has to be, and let's think about why. X minus 1, you can't have a negative in underneath the radical and have a real number. So x minus 1 has to be greater than or equal to 0, which means x has to be greater than or equal to 1. So that's why that happens. So it's important that you understand that. And then for our range, we're just going to kind of use our graph, although we can use this value right here. Notice the k is a 2 and it's going up. So y is greater than or equal to 2. And that would be our domain and range. So this idea here is really important. The radicand, which is what is called underneath the radical, the radicand has to be greater than or equal to 0. So next problem. All right, so this one, I want you to think about this. If the locator point, -3, -1, so you should be able to get that, then what does this 2 right here do? Remember, it still doubles the ups. It doubles the ups of our parent graph. Now, this over here was like our parent graph, but now we're going to double the ups. And even though I know this wasn't the parent graph, but it wasn't stretched or compressed, so the movements were like the parent graph. So here, my locator point, I have that. then over 1, and instead of up 1, I'm going to go up 2 because I'm doubling the ups. Then I go over 4 because that's what I'm doing for the square root graph. And instead of up 2, I double that and I go up 4. So I'm going to do my locator point, -3, -1. From there, notice it is opening up, or it's going up. So then I'm going to have over 1, up 2, and over 4, up 4. And this is my graph. My domain, remember this x plus 3 has to be greater than or equal to 0, which means x has to be greater than or equal to -3. And you can tell that from looking at your graph as well. And for the range, it's about this -1. So y is greater than or equal to -1 because it's going up. And then for our last one, the locator is going to be a +2, +1. So I'm going to locate that. Now this one, notice, it's going to have the same movements, except we're going to go down. So it's not stretched, but it's going to go down instead of up. It's flipped over. It would be, well, it's just going to it would be flipped over the x-axis. So from here, we're going to go over 1, and instead of up 1, we're going to go down 1. And then I'm going to go over 4, and instead of up 2, I'm going to go down 2. So this one wasn't stretched, so it was like the parent graph movements. And so I get this. And you could, again, make a table of values on your calculator if you need to. That's fine. The domain, we still have to say that x minus 2 is greater than or equal to 0, which means x is greater than or equal to 2. And the range, this time it's going to be less than, so y is less than or equal to the k value, which was 1, because notice it's going down instead. So what does this graph do, and what's different about it? Notice that my 2 is not on the outside, it's on the inside. So what impact does this have? This doesn't really fit into the ones that we've been looking at. So, but I want to explore that. Because the locator point, you might think the locator point is 1, 3, but it's not. So here's what we have to think about. When we consider the domain, remember the radicand, the part under the radical sign, has to be greater than or equal to 0. Well, I have a 2 in there now. 2x minus 1 is greater than or equal to 0. So when I solve this, I get that x has to be greater than or equal to 1/2. That actually is the x value for my locator point. So when you have a number in front of the x like that, a coefficient, then you can't just take the opposite of this. You have to divide by what's in front. So my locator point for this one is going to be a +1/2, and it's still going to be a +3. So it's going to be here instead. So I'm counting by ones. I haven't said that on any of my graphs. Now, and then you might look at this and say, oh, it's not stretched, but it is stretched. And you might say, how could you say that? What's in front of the x? Well, the square root of 2. So this is actually stretched, vertically stretched, by the square root of 2. So this one, I would not have you do, have over 1 up, the square root of 2, where you would actually use your calculator and a table of values to come up with this. You do know that because it's a positive here that it's going to open up. So we could take a minute and look at our calculators and see what we get. So let's do that. Let me clear out what we had here before. So if we take a look at the square root of 2x minus 1 plus 3, and we'll graph that. Okay, so we can see this. Now it's going to be kind of hard to tell here, but if you wanted to go ahead and look at a table of values, notice I have error for all these values. Well, that's because we said x has to be greater than or equal to 1/2. So notice once I get to 1/2, and that's because I actually had my graph. Let me show you on table set. If I had had my delta table set to say 1, and then I looked at my table, notice that I don't see the half on there anymore. So if I want to be able to see the half and be able to draw an accurate graph, then your delta table is basically telling you what to count by, what your increment should be, what are your step increments. So by making it 0.5, then I know I'm going to catch that, that value of a half. So then what you could do is you could just plot some points. For example, I'm going to plot the 0.14 because that's easy. So if I plot the 0.14, and then I'm going to go back over here and scroll down some more. Ooh, 2.55, that one looks easy to graph. So I'll do that one, and I'll see if I can get one more that's easy. 5.6 looks pretty easy to graph. And that's enough that I can tell the shape. I am perfectly fine with you doing that. I would prefer, if you are going to graph using that method with a table of values, tell me the points that you plotted. So just, make a quick little graph of that. So this was it for your video today. And you're going to be turning in your notes to me, and then we'll have a follow-up assignment tomorrow from your textbook where you will be doing some of these problems. So that is it for today.